Capillary action is the ability of a liquid to flow in narrow spaces without the assistance of, and in opposition to, external forces like gravity. The effect can be seen in the drawing up of liquids between the hairs of a paintbrush, in a thin tube, in porous materials such as paper, in some non-porous materials such as liquefied carbon fiber, or in a cell. It occurs because of intermolecular forces between the liquid and surrounding solid surfaces. If the diameter of the tube is sufficiently small, then the combination of surface tension and adhesive forces between the liquid and container act to lift the liquid. In short, the capillary action is due to the pressure of cohesion and adhesion which cause the liquid to work against gravity. History. The first recorded observation of capillary action was by Leonardo da Vinci. A former student of Galileo, Niccolo Aggienta, was said to have investigated capillary action. In 1660, capillary action was still a novelty to the Irish chemist Robert Boyle, when he reported that some inquisitive French men had observed that when a capillary tube was dipped into water, the water would descend to some height in the pipe. Boyle then reported an experiment in which he dipped a capillary tube into red wine and then subjected the tube to a partial vacuum. He found that the vacuum had no observable influence on the height of the liquid in the capillary. So the behavior of liquids in capillary tubes was due to some phenomenon different from that which governed mercury barometers. Others soon followed Boyle's lead. Some thought that liquids rose in capillaries because air couldn't enter capillaries as easily as liquids, so the air pressure was lower inside capillaries. Others thought that the particles of liquid were attracted to each other and to the walls of the capillary. Although experimental studies continued during the 18th century, a successful quantitative treatment of capillary action was not attained until 1805 by two investigators, Thomas Young of England and Pierre-Simon Laplace of France. They derived the Young-Laplace equation of capillary action. By 1830, the German mathematician Carl Friedrich Gauss had determined the boundary conditions governing capillary action. In 1871, the British physicist William Thomson determined the effect of the meniscus on a liquid's vapor pressure, a relation known as the Kelvin equation. The German physicist Franz Ernst Neumann subsequently determined the interaction between two immiscible liquids. Albert Einstein's first paper, which was submitted to Annalen der Physik in 1900, was on capillarity, phenomena and physics of capillary action. A common apparatus used to demonstrate the first phenomenon is the capillary tube. When the lower end of a vertical glass tube is placed in a liquid, such as water, a concave meniscus forms. Adhesion occurs between the fluid and the solid inner wall, pulling the liquid column up until there is a sufficient mass of liquid for gravitational forces to overcome these intermolecular forces. The contact length between the top of the liquid column and the tube is proportional to twice the radius of the tube, while the weight of the liquid column is proportional to the square of the tube's radius. So, a narrow tube will draw a liquid column higher than a wider tube will, given that the inner water molecules cohere sufficiently to the outer ones. In plants and trees, the capillary action is enhanced in trees by branching, evaporation at the leaves creating depressurization, and probably by osmotic pressure added at the roots and possibly at other locations inside the plant, especially when gathering humidity with air roots. Examples. Capillary action is essential for the drainage of constantly produced hair fluid from the eye. Two canal liculi of tiny diameter are present in the inner corner of the eyelid, also called the lacrimal ducts. Their openings can be seen with the naked eye within the lacrimal sacs when the eyelids are everted. Wicking is the absorption of a liquid by a material in the manner of a candle wick. Paper towels absorb liquid through capillary action, allowing a fluid to be transferred from a surface to the towel. The small pores of a sponge act as small capillaries, causing it to absorb a large amount of fluid. Some textile fabrics are said to use capillary action to wick sweat away from the skin. These are often referred to as wicking fabrics, after the capillary properties of candle and lamp wicks. Capillary action is observed in thin-layer chromatography, in which a solvent moves vertically up a plate via capillary action. In this case, the pores are gaps between very small particles. Capillary action draws ink to the tips of fountain pen nibs from a reservoir or cartridge inside the pen. With some pairs of materials, such as mercury and glass, the intermolecular forces within the liquid exceed those between the solid and the liquid. So a convex meniscus forms and capillary action works in reverse. In hydrology, capillary action describes the attraction of water molecules to soil particles. Capillary action is responsible for moving groundwater from wet areas of the soil to dry areas. Differences in soil potential. Theta is the contact angle, ρ is the density of liquid, g is local acceleration due to gravity, and d is radius of tube. Thus the thinner the space in which the water can travel, the further up it goes. For a water-filled glass tube in air at standard laboratory conditions, gamma equals 0.0728 N per meter at 20 degrees Celsius, theta equals 0 degrees equals 1, ρ is 1000 kilograms per cubic meter, and g equals 9.81 meters per square second. For these values, the height of the water column is thus for a 4 meters diameter glass tube in lab conditions given above. The water would rise an unnoticeable 0.007 millimeters. However, for a 4 centimeters diameter tube, the water would rise 0.7 millimeters, and for a 0.4 millimeters diameter tube, the water would rise 70 millimeters. Liquid transport in porous media. When a dry porous medium, such as a brick or a wick, is brought into contact with a liquid, it will start absorbing the liquid at a rate which decreases over time. For a bar of material with cross-sectional area A that is wetted on one end, the cumulative volume 5 of absorbed liquid after a time t is where S is the sorptivity of the medium, in units of ms-1/2 or mm-1/2. The quantity is called the cumulative liquid intake, with the dimension of length. The wetted length of the bar, that is the distance between the wetted end of the bar and the so-called wet front, is dependent on the fraction f of the volume occupied by voids. This number f is the porosity of the medium. The wetted length is then. Some authors use the quantity S, f as the sorptivity. The above description is for the case where gravity and evaporation do not play a role. Sorptivity is a relevant property of building materials, because it affects the amount of rising dampness. Some values for the sorptivity of building materials are in the table below.